In modern physical cosmology, the cosmological principle is the notion that the distribution of matter in the universe is homogeneous and isotropic when viewed on a large enough scale. Since the forces are expected to act uniformly throughout the universe, and should, therefore, produce no observable irregularities in the large-scale structuring over the course of evolution of the matter field that was initially laid down by the Big Bang. Astronomer William Keel explains, the cosmological principle is usually stated formally as, viewed on a sufficiently large scale, the properties of the universe are the same for all observers. This amounts to the strongly philosophical statement that the part of the universe which we can see is a fair sample, and that the same physical laws apply throughout. In essence, this in a sense says that the universe is knowable and is playing fair with scientists. The cosmological principle depends on a definition of observer, and contains an implicit qualification and two testable consequences. Observers means any observer at any location in the universe, not simply any human observer at any location on Earth. As Andrew Liddell puts it, the cosmological principle means that the universe looks the same whoever and wherever you are. The qualification is that variation in physical structures can be overlooked, provided this does not imperil the uniformity of conclusions drawn from observation. The Sun is different from the Earth. Our galaxy is different from a black hole. Some galaxies advance toward rather than recede from us. And the universe has a foamy texture of galaxy clusters and voids. But none of these different structures appears to violate the basic laws of physics. The two testable structural consequences of the cosmological principle are homogeneity and isotropy. Homogeneity means that the same observational evidence is available to observers at different locations in the universe. Isotropy means that the same observational evidence is available by looking in any direction in the universe. The principles are distinct but closely related, because a universe that appears isotropic from any two locations must also be homogeneous. Origin. The cosmological principle is first clearly asserted in the Philosophy and Naturalis Principia Mathematica of Isaac Newton. In contrast to earlier classical or medieval cosmologies, in which Earth rested at the center of universe, Newton conceptualized the Earth as a sphere in orbital motion around the Sun within an empty space that extended uniformly in all directions to immeasurably large distances. He then showed, through a series of mathematical proofs on detailed observational data of the motions of planets and comets, that their motions could be explained by a single principle of universal gravitation, that applied as well to the orbits of the Galilean moons around Jupiter, the Moon around the Earth around the Sun, and to falling bodies on Earth. That is, he asserted the equivalent material nature of all bodies within the solar system, the identical nature of the Sun and distant stars, and thus the uniform extension of the physical laws of motion to a great distance beyond the observational location of Earth itself. Implications. The cosmological principle represents both the principle on which cosmological theory and observation can proceed and null hypothesis of uniformity that is an area of active research inquiry. Many important advances in astronomy and cosmology, and the formulation of new cosmological theories, have occurred through the resolution of apparent violations of the cosmological principle. For example, the original discovery that far galaxies appear to have higher spectral redshifts than near galaxies led to the discovery of Hubble flow, the metric expansion of space that occurs equally in all locations. Because this history is currently described almost entirely in terms of known physical processes and particle physics, the cosmological principle is extended to assert the homogeneity of cosmological evolution across the anisotropy of time. All points in space ought to experience the same physical development, correlated in time in such a way that all points at a certain distance from an observer appear to be at the same stage of development. In that sense, All spatial conditions in the universe must appear to be homogeneous and isotropic to an observer at all times in the future and in the past. That is, earlier times are identical to the distance from the observer in spacetime, which is assessed as the redshift of the light arriving from the observed celestial object. The cosmological principle is preserved because the same sequence of evolution is observed in all directions from Earth, and is inferred to be identical to the sequence that would be observed from any other location in the universe. Observations show that more distant galaxies are closer together and have lower content of chemical elements heavier than lithium. Applying the cosmological principle, this suggests that heavier elements were not created in the Big Bang but were produced by nucleosynthesis in giant stars and expelled across a series of supernovae explosions and new star formation from the supernovae remnants, which means heavier elements would accumulate over time. Another observation is that the furthest galaxies are often more fragmentary, interacting and unusually shaped than local galaxies, suggesting evolution in galaxy structure as well. A related implication of the cosmological principle is that the largest discrete structures in the universe are in mechanical equilibrium. Homogeneity and isotropy of matter at the largest scales would suggest that the largest discrete structures are parts of a single indiscrete form, like the crumbs which make up the interior of a cake. At extreme cosmological distances, the property of mechanical equilibrium in surfaces lateral to the line of sight can be empirically tested. However, under the assumption of the cosmological principle, it cannot be detected parallel to the line of sight. Cosmologists agree that in accordance with observations of distant galaxies, a universe must be non-static if it follows the cosmological principle. In 1923, Alexander Friedmann set out a variant of Einstein's equations of general relativity that described the dynamics of a homogeneous isotropic universe. Independently, Georges Lemaitre derived in 1927 the equations of an expanding universe from the general relativity equations. Thus, a non-static universe is also implied, independent of observations of distant galaxies, as the result of applying the cosmological principle to general relativity. Justification. Although the universe can seem inhomogeneous at smaller scales, it is statistically homogeneous on scales larger than 250 million light-years. The cosmic microwave background is isotropic, that is to say that its intensity is about the same whichever direction we look at. However, the European Space Agency has concluded, based on data from the Planck mission showing hemispheric bias in two respects. One with respect to average temperature, the second with respect to larger variations in the degree of perturbations, i.e., temperature fluctuations, i.e., densities, that these anisotropies are, in fact, statistically significant and can no longer be ignored. Criticism. Karl Popper criticized the cosmological principle on the grounds that it makes our lack of knowledge a principle of knowing something. He summarized his position as follows: the cosmological principles were, I fear, dogmas that should not have been proposed. The cosmological principle implies that at a sufficiently large scale, the universe is homogeneous, different places will appear similar to one another, whilst Yadav al. have suggested a maximum scale of 260 HMPC for structures within the universe according to this heuristic. Other authors have suggested values as low as 60 HMPC. Yadav's calculation suggests that the maximum size of a structure can be about 370 MPC. The Claus-Campusano LQG, discovered in 1991, has a length of 580 MPC, and is marginally larger than the consistent scale. The Sloan Great Wall, discovered in 2003, has a length of 423 MPC, which is only just consistent with the cosmological principle. U-1.11, a large quasar group discovered in 2011, has a length of 780 mpc, and is 2 times larger than the upper limit of the homogeneity scale. The huge LQG, discovered in 2012, is 3 times longer than, and twice as wide as is predicted possible according to these current models, and so challenges our understanding of the universe on large scales. In November 2013, a new structure 10 billion light-years away measuring 2,000 to 3,000 mpc has been discovered, the Hercules corona Borealis Great Wall, putting further doubt on the validity of the cosmological principle.